So this is 6.3 numerical model. So what is the numerical model? The numerical model uses numbers and results from tests to compare certain aspects of a performer's attributes and can be used to create an ideal model with the ideal components for their sport. It uses tests and components such as kinematics and kinetics. Kinematics being different motions, for example, linear motion and angular motion. Linear motion being motion in a straight line, angular motion rotating around a pivot point, and kinetics being force production to create a movement. This can be on objects or on the ground to create motion in sport. As just mentioned, this is a quantitative method as it uses numbers and values to analyze performance. To create this model, data can be drawn from literature and elite athletes to form a number of ideal scores, basically, that these people have got in their tests, and these scores represent the ideal amount of force, for example, needed in, say, rebounding for basketball, or the ideal speed to get up the court in a three-quarter sprint, in linear motion, for that sport. So it creates the perfect or the ideal force or the ideal speed needed for that sport. So as mentioned previously, forces can be used to help create the numerical model. Now forces can be a push or pull that alters the state of motion of a body. So in this image here, it's a push or pull. And if there is no push or pull, then the object will stay still. It's not moving. There's no force applied to it. But if you create a force through push or pull, you create movement. Now, there are many effects of force on objects. First being rest to move, as I just kind of explained. If something's still, it's not got any force, but when you apply force to it, you create movement, you create motion. So also another example would be muscle contraction. When you're standing still, you're not, well, I guess you are contracting to stay up, but to move forward, your muscles must contract in order to propel you forward. Forces can also change direction. For example, the backboard in basketball, the thing behind the rim. When you shoot the ball, if you shoot on the corner of the backboard, the ball will hit the backboard and change direction, and the backboard acts as a force. The ball hits the backboard with a force, the force you apply to it to shoot the ball then applies that force to the backboard, and that backboard and the angle that it hits changes the direction of the ball and changes the direction of the movement. So another effect would be acceleration. Forces, when applied to something, can accelerate the object. So for example, in a car, when you move your foot down on the accelerator, you're applying a force. The engine is applying a force to the wheels then spin, creating acceleration, moving off from 0 to however fast you push down on the accelerator, which means however the bigger force. So bigger the force, more acceleration. So then another one, the opposite to that, deceleration. So when a force is applied, it can also decelerate. So another one would be the backboard example as well. So when the ball hits the backboard part, the velocity of the ball will change because it's not going, depending on the composite of the backboard, of course, it will slow down the ball. Also in this picture here, when the tennis ball hits the ground, it changes shape. So that's also another one. forces can change shape. So as you can see here, the ball is squished. The changing of shape releases energy. Basically, the force and the change of the shape of the ball releases energy, which decelerates the object, as less energy is then used to bounce back up. So that's why when you drop a ball, it doesn't continuously bounce. It slows down because there's deceleration and loss of force, loss of energy. Yeah. So those are the 5 effects of forces. So when we talk about force, it's important that we talk about Newton's 3 laws of motion, as these can be applied to everything really when we talk about force. So Newton's first law is the law of inertia. This is kind of what I said before, actually, with saying that everything has a reluctance to change unless a force acts upon it. So you're standing still, you will not move, or an object will not move unless there is a force applied to it. It will stay still, and that is the law of inertia. It has a reluctance to change. So, for an example, a basketball won't bounce without a force applied to it. If it's just sitting there on the floor, it will not move, it will not bounce unless a player acts on it, creating a force for it to bounce. Otherwise, it will just sit there and it won't do anything because of Newton's first law. If 2 forces are opposite and acting on each other, there will be no change in force. So for example, if 2 cars are head-on and they both start accelerating at the same acceleration, they stay in the same acceleration, they won't move. They'll stay where they are because they're acting against each other with the same amount of force. So there will be no change. Yeah. So on to Newton's second law. This is the law of acceleration. Also, kind of I touched on this just now. Acceleration. It states that acceleration is proportional to the size of the force applied. So also, like I said, if there is a bigger force applied to an object, then there will be more acceleration. Also, acceleration takes place in the direction that the force acts. So for this example, here, the player is in an upward motion, jumps in an upward motion. So that's the way they accelerate upwards. Yes, and also it states that a greater mass. So if a player is more heavy, there will be less acceleration. That's why many players are more nimble and have more muscle in order to create more force. So also another example of this is a car and a truck. I mean, which one's going to accelerate quicker? It's going to be the car because it has less mass, it's less heavy, so it doesn't need as much relative force to accelerate. Okay, so the last one, Newton's third law. This is the law of action and reaction. So every force applied will have an equal and opposite reaction. So using this example here, jumping in basketball, the player acts and creates a downward force into the ground. Now the equal and opposite reaction here is the ground then propelling him upwards and creating the same force. It's equal. So the force that he applies downwards is the amount of force that the ground will accelerate him upwards. And this can be said for running as well. One foot in front of the other. When you push into the ground when running, it will create a force depending on your foot positioning as well. That's also a big thing. So runners will adapt the way they run in order to propel themselves forward with their foot positioning. So they would want to push into the ground kind of in a backwards motion, so the ground propels them forward, making them running efficiently. And this can be This can be also applied to basketball and that, because running is important in basketball, and running and being quick. So players may also use this to increase their speed and their efficiency. So when it comes to basketball, measuring force is very key in terms of creating an ideal numerical model. Basketball is a very force and power related sport. There's lots of bounding, there's lots of powerful movements, explosive movements at the basket and away, and playing defense. So measuring a player's force production can be quite helpful to understand the level of force needed to be successful in the sport. And I'll go on to good ways to measure force just in a little bit. So another component of the numerical model is, this component can be used to, like force, can be used to help create the numerical model, is linear motion. Now linear motion is movement of the body in a straight line, and all parts of the system move in a straight line. And this again, an example of this is running and sprinting. That's in a linear motion. So using that to understand basketball is important. So types of linear motion can be vector and scalar quantities. So scalar only describes the magnitude, only has one measurement, whereas a vector quantity describes magnitude and direction. So it has two measurements. So examples of these are speed and velocity. The speed being the vector, speed being the scalar, and velocity being the vector. And also distance and displacement. Distance being the scalar, and displacement being the vector. So these act in linear motion and can be measured. So distance is the sum of all movement regardless of direction, and displacement takes this into account. So it takes the direction into account and measures the straight line distance they have traveled, whereas distance only tells you how far they've traveled, whereas displacement can tell you how a straight line to get there. So for example, on this graph down here, a player could have run along this line here and down here to 3, and that would be their distance. That would be the number you get when measuring distance. However, displacement would take into account where they started and where they finished. So it would use this measurement of the straight line and would tell you basically the quickest path that they could have taken, which could help reduce time and reduce the amount of energy spent. So displacement in this sense can be an important measure, because it can help players understand what they're wasting. They may be wasting their energy doing a path that is too long, and they can use displacement to show a quicker path. So speed is a scalar quantity that measures how fast the body moves, whereas velocity takes direction into account as well and measures how fast they're going in and what direction. This allows for acceleration and deceleration to be shown using distance time graphs and acceleration time graphs, velocity time graphs as well. These graphs show speed in a particular moment. The distance time graph shows speed in a particular moment. That's the gradient of the distance time graph. So that's this graph here. The gradient shows the speed. So the red line is slower than the blue line, and as the gradient is higher. And these are useful in biomechanics to help explain and compare players in their speed and distance they create. Sorry, the video is going to cut out here, so I'm going to stop there and create the next one.